ננסה. Okay, so let's remind ourselves quickly what we did last time. So last time we left all the discussion about static fields, okay, and we introduced time as a new degree of freedom in the Maxwell equations that we wrote, and we saw that from these Maxwell equations we remained in vacuum, okay, and we saw that we can derive wave equations from the Maxwell equations, and once we had these wave equations, we asked, okay, what is the structure of the electromagnetic waves in vacuum, if you remember, and we made all kind of comments about the structure, the shape of the electromagnetic waves in vacuum, and we saw that there is one formula that can summarize everything that we said. If you remember, we said that B is orthogonal to the direction of the propagation, and it's orthogonal to E, and we said that E is orthogonal to both only in vacuum, etc. And we said that all of these things can be summarized. So here are just reminders from last time, okay? From last lecture. Okay, we saw that everything that we wrote can be summarized with the following equation. Okay, where of course C0 is the velocity of light in vacuum. Okay, and then at the very end we also introduced the pointing vector. And if you remember, so we defined it in the following way. By the way, when you heard of it, was it noted by or S? S? Okay. So generally speaking, it's good to learn the same things again with different notation. Okay. If we release ourselves from the notation, it means we really know something. But I know it's sometimes referred to as S. And if you remember, we didn't start from the definition of the pointing vector. What did we do? You remember? We did.
The vector sign over pi because it's also a vector.
Yes. So how did we introduce this? You remember? Was it? Yes, so we also showed that from the Maxwell equation we can write conservation's equation for the charges. Remember, we wrote something like this. Okay, we saw that we reminded ourselves that this is a continuity equation, an equation that tells me that some quantity is conserved, and in this case it's the charge. And I would need an additional source term if I had a source term for the charge, remember? And then we wrote something similar for the energy. I told you, I reminded you, I assumed that we all know that in a volume V where I have an electromagnetic field, there is an energy density which I called rho electromagnetic, is the density of energy, which I can write in the following way. Okay, and this I didn't show again. I assumed you know it from the previous lecture. I will write you I think it's in the Griffiths in chapter 7 to 4, okay, in case you need some refreshing on why this is true, but generally speaking, if I have an electromagnetic field with E and B in a volume V, I have some energy in this volume, and this energy is given by this equation, okay? And we convinced ourselves that Ej, okay, is the energy that moving charges receive from the electromagnetic field in the shape of work. Okay, remember we also said this. So so this is the work. We showed this very quickly, received by charges, by moving charges, from the electromagnetic field, okay? And then what we did is we opened this. I'm reminding this because we did it very quickly at the end of the lecture. We opened this, okay? And we managed to write, we opened this, and we found ourselves with the following equation: div of E equals B divided by mu 0 plus dt of half mu 0 B square plus half epsilon 0 E square plus Ej is equal to 0. Okay, so we got this equation, and then what we said is that this equation is actually a conservation equation for the energy, okay, in the same way that this is a conservation equation, where this is my source term, okay, it's the work I receive, the sourcing term, okay, and this is rho Em, okay, and this allowed us to interpret this as what? As the energy density, no, sorry, yes, as the J, okay, J of energy transported by the field by the field per unit, okay? J is always per unit of time and unit of surface, remember? Okay? Per unit of time and area, okay? And this is what we call the point. So rather than defining it, we obtained it from a conservation equation on the energies. Okay? So now what we will do, I'm telling you the plan for this lecture. In the first half hour or so, we will say additional things about the Poynting vector, what we can learn from it, some specific properties of the Poynting vector in the case of plane progressive waves and in the specific case of harmonic waves. Okay, and then in the same way that we did in electrostatic, we will move on to talk about waves in materials, okay, and we will ask in the same way that we wrote wave equations from the Maxwell equation in vacuum, can we do the same in a material? Is there such thing at all as an electromagnetic wave in vacuum? And if yes or no, how does it differ from, in material? Confused. You got it, what I said? We will write the Maxwell equation in material. We will ask, do we have some waves at all in material? And what are the difference between what propagates in waves and what propagates in materials? Okay, so let's start by some properties about the Poynting vector in vacuum. So this is still from the this is still under the chapter electromagnetic waves. Okay. Can I erase this? Okay, so some properties of P in vacuum. Okay, and I want you to keep in mind all the time that P is the vector that describes how energy is transported in vacuum. Okay, so first property, P is in the direction UK, okay, the direction of propagation, okay, and if I had to show it, a very quick demonstration of this. How do I see it that P, that the Poynting vector is in the direction of the wave?
Because according to the Maxwell equations, the three vectors are, like the vector for the motion, the vector for electric field, and the vector for magnetic field are all perpendicular to each other as the Poynting vectors.
Right, so if I summarize what I said, I have that the Poynting vector is given by this, and okay, so it's perpendicular to both, and we started by saying that E plus C0 UK cross B equals 0, okay, so these two equations give me the fact that the Poynting vector is in the direction of the wave. Second property, okay, and I also strongly recommend that at home you make yourself some summaries of what is true in vacuum, what is true in materials, what is true for plane progressive waves, and what is true for harmonic waves. Okay, I will do a distinction in a second. Okay, so another property is that in every point in space and time, the Poynting vector is proportional to E square. Okay, so this is just another way to write the Poynting vector. Okay, so let's show it. Okay, so I'm using this. Okay, in terms of values is 0b. And by the way, this reminds us that in terms of value, E is much larger, is much higher than the values of E are much higher than the values of B, right? Okay, so I can write. I'm just writing here this cos 0 E divided. Okay, and this is just a one-line demonstration. Okay, and this 1 over C0 mu 0, this is also equal to C0 E0 epsilon 0. This. Okay, you can show this very easily. Okay, so I can replace this by C0 epsilon 0, and I'm getting this equation. Okay, another interesting property, do you remember how does the energy divide itself between the fields, the various fields? Maybe last time you heard about the Poynting vector. So let's write it. So for plane, so PPW is plane progressive wave. If you remember, when we started talking about waves, we saw that the most general solution for the wave equations were the function of this shape. You remember? So these are plane progressive waves, okay? And then we saw a very specific case, a special case of this function where f is a cosinus or a sinus, okay? Which are harmonic waves. And so on the one hand, all the solution of the waves equation can be written like this, and on the other hand, because of Sturm-Liouville, you can write all the functions as sums of cosinus and sinus. So each of these functions have their own advantages, but they are different. So now I'm making a clear distinction between these functions, and what I'm saying now is in the general case of plane progressive waves. Okay, so for this kind of wave, I have an equipartition of the energy. Okay, and what does it mean? It means that the energy transported, the transport of energy described by the Poynting vector, is divided equally between the electric field and the magnetic field. And this is not so intuitive because of this, right? In terms of the values of the fields, okay, the values of E are much higher than the values of B, but in terms of energy, they spread evenly. So let's show this. Okay, so I know that rho EM is equal to this. This again I'm assuming, but we all know. Okay, and this is also 1/2 mu 0 E square over C0 square. Okay, so this is 1/2 mu 0 E square 1/mu 0 epsilon 0. Okay, so this is also half of epsilon 0 E square. Okay? So this will be equal to, so it's half plus half, epsilon 0 E square. Okay? And this is not obvious because B is much smaller than E. Okay, but in terms of energy, they'll spread, the energies are spreading evenly on the two contributions from both fields. Okay, and now the fourth thing that I want to say is, and the fourth and last property I want to say about the Poynting vector is going to be specific to harmonic functions. Okay, the very specific case of harmonic functions. So for harmonic plane progressive waves, okay, harmonic plane progressive waves. Do you remember something about the mean value of the Poynting vector? Does it ring a bell? No? Okay, so what I'm going to try to show now is that for a harmonic plane progressive wave,
not obvious inequality, but B and E have different units.
Yes, it's true. I was going to say that this inequality is not very orthodox because we're comparing apples and oranges, but when I'm trying, so I'm going to put some Verschain, okay? Okay, the point here is that norm-wise, value-wise, if you take the vectors, the values in E are much higher than the values in B, but still, if you convert it into energies, the values are equal, okay? This was my point. But I agree with you, this is an inhomogeneous inequality, it's not a real one. Okay, Okay, so for harmonic plane progressive wave, I'm also going to say something that is, I think, is not obvious. The average value of the Poynting vector, okay, the average value of whatever describes the travel of energy, okay, is constant. I'm going to show it now, but this too is not obvious because we're talking about waves. So E and B are changing all the time, right? Remember last time we showed, I showed you this small movie where you see E and B varying simultaneously, etc. So what we are claiming here is that on average, whatever describes the travel of energy is going to be constant for harmonic waves. Okay, so let's show it. And constant in space. Okay, so the mean value of P, I'm going to tell you the value of it, is constant. Okay, and I'm going to show you that I'm given by half of epsilon 0 C0 E0 square UK, where E0 is the amplitude of the wave. Okay, so this doesn't, there is no time dependency and there is no space dependency here. Okay? So let's show this. Okay, so I'm not writing it in a complex shape because I'm going to use the well-known fact that the average of cos square is half. Okay, so I'm remaining in real notation. Okay, so E, let's write it down. So E, I have some amplitude, some wave on X and some wave on Y. Okay, so let's just write it. Minus kz minus some phases that is specific to the x component, ux. Okay, this is a unitary vector along the x direction. Okay, plus E0 y cosinus of omega t minus kz. Okay, this is z here, is the direction of the propagation. Minus phi y u y. Okay, and if I square this, I will have E0x square, a square of cos, which I'm not developing, plus I will have this square too, okay, plus 0 because ux and uy are orthogonal. Okay, so I don't have any cross terms. Okay, and so if I take the average of the Poynting vector, this is, I'm using the result I showed in the general case. This is going to be epsilon 0 C0 E square UK, right? So I can take this out of the average. UK, okay? And this is going to be epsilon 0 C0 half of E0x square plus E0y square, okay, which is UK, which is E0 square. Okay, so I just, also just a few lines and I showed this. Okay? Okay, so this ended the 4 comments I wanted to make on the Poynting vector. Okay, something about its direction, something about its value, and then 2 more physical comments, one about the equipartition of the energy between the fields, and one about the average value in the specific case of a harmonic function. Okay? So now we will move on to talk about electromagnetic waves in materials, if such thing exists at all. Do you have an intuition? Do you have some things you remember about it? What happens to electromagnetic waves in materials, in matter? No? Nothing? Or just being shy? אתם זוכרים מזה משהו או שלא למדתם על זה בכלל?
בגלים הגלים שכאילו...
זהו, אני אף פעם לא יודעת בדיוק מה היה בגלים, מה בחשמל. Okay, so I will assume you know nothing about it. Okay, so I have a new chapters, waves in materials. Okay, and in order to derive, to say all the things that we want to say, we need to remind ourselves the basic concepts that we introduced when we talk about electromagnetic fields in matter. So, if you remember, we had several kinds of materials, of the electric materials. We had some that were polar and some that were apolar, okay? Do you remember what were in the polar ones, like water, for example, do you remember what was the story about them? Okay, so I'll remind it. So in the polar materials, we had some intrinsic dipoles. Okay, the example I gave was water, but they were oriented in all kinds of directions. And then when I was applying an external electromagnetic field, they would all align in the same direction. Okay, so the polarization was resulting from the alignment of all these dipoles. And in apolar materials, I didn't have any intrinsic dipole in the matter, but the molecules would stretch, okay? The atoms and the molecule there would be some level of stretching. And when I applied, we talk about the fact that, in fact, materials are never neutral, okay? At the microscopic level, I have some charges, but they are bound. The charges are bound around within the atom, okay? And we talked about the fact that this stretching was leading to a dipole, to many, many small dipoles, and we defined what we call the polarization. Okay, so so we had polar and apolar. I'm just reminding the concept. Okay, so here I had intrinsic dipole aligning, and then here I had stretching of atoms or molecules. Okay, and we defined a small within a volume d tau. Okay, we defined a small dipole, and we said that it's annoying that I have small p and big P, but this is how things are always written. So, which is the sum of some permanent dipole, plus induced dipole. Okay, and we define the polarization, which is large P, like the volume density of all these dipole. Okay, so we wrote that it's the limit when d tau go to 0 of did P, it's this one over d tau. Okay, and this was also rho n pi, where this is the average or common dipole. Okay? Okay, so these are the things that we already know from talking about electrostatics in material. And now we're going to ask what happens to this polarization when the fields are varying in time. Okay? Okay, now when we talked about polarization in electrostatics, if you remember, we drew the center of mass of the positive charges and the center of mass of the negative charges. I had like a cloud of electrons. And then when we talked about the stretching, we talked about how these center of mass are going apart from each other, and this is how we defined the atomic dipole. But at the time, we didn't care, and we said it, we didn't care about how long it takes to this equilibrium to be reached, right? We just looked at the final, the equilibrium stage, exactly, where the charges are still bound, and they went as far as they can from each other, and they're not moving anymore. And now one of the main things that will change is that because the fields are varying, I will need to consider the times that it takes for these dipoles to form. Okay, so I have these are the center of mass of the positive and negative charges. Okay, so. And now the distance between them will vary in time. Okay, this will vary in time. This is the main difference with the static case. Okay, and this will lead to some density of current, J, which will be given by dp over dt. This is large P. Okay, this is very important, we will need it. Okay, so I will give you some, I'm not doing the some detailed rigorous demonstration, but I'm giving you the main points. So if you remember, we defined an element of current DC. This is the same DC that we used in Biot-Savart. Okay, if you remember, 4 pi DC Q. Okay. Okay, so DC, this is J d tau by definition. Okay, and J is equal to rho V in this case, where rho is the density of charges. Okay, but the V I'm looking in this case, okay, I'm looking at the movement of charges that appears from the movement of from the relative movement of the negative and positive charges inside the atom. Okay, makes sense? So V here is equal to dNP over dt. Okay, and I can write this as rho n. This is the number density, okay? This is the charge density. אתה מבין? אני רואה אותך כזה, עושה עם הגבות. כן? So, rho n dq. Okay, and this, by definition, is the small dipole, the atomic dipole. So this is rho n did pi. It's actually a fair demonstration. Okay, and this is did d of depolarization over dt. Okay, so makes sense? Okay, I wrote the definition of J. Okay, J is rho v when I have some volume, where rho is the density of charge and v is the velocity, the movement of some measure of the movement of these charges. Okay, and the specific velocity that I'm looking here is the one that arises from the fact that when I apply some changing electromagnetic field on the atom, the center of masses of the negative charges and the positive charges will change compared to each other, okay? Their position will change. So this is the velocity I'm looking at, okay? And this allows me to write it as a function of the average individual dipole at the scale of the atom, okay? And this is how the polarization appears in my equation, okay? So this was just to show this, and this is important. I will use it. I will use it now. Okay, and in the case, I will. Can I raise this? In the electrostatic case, if you remember, we said that we don't want to deal with the polarization. We don't really know how to deal with bound charges. Okay, what we know how to deal with is density of charges, either volume density or surface density. Okay, so we showed that rho bound, that we have some volume density and surface density which appear following the polarization of the material. Do you remember how we wrote them?
Minus divergence.
Right? And the sigma band was equal to P and X. Exactly. Okay, you remember how we showed it? We wrote the potential as a function of the polarization, and then we have two terms, one volume term, one surface term, and we did some identification, and we said, okay, this must be a volume density, and this must be a surface density. Okay, so we have also this formula that will be useful. Okay, so I'm going to assume that these are still true. We're going to accept that these are still true in our case and I will give you some justification, at least for this part. Okay, so if I write the conservation equation, J plus dt rho. Okay, I can write this, and this is why it was so important to derive this. So I can write div of J like did P over dt. So this is div of P plus rho. Okay. And so this means that this is a constant, right? And for continuity reasons, it also has to be zero. Because before I apply Okay, this is the argument on why I can use these two formula, which I showed rigorously in the static case. Why can I use them in the dynamic case? Okay, and what I'm saying is that I can write a continuity equation. Okay, and it leads to the following: that div of p plus rho has to be constant. Okay, but before I apply the changing the dynamical field, this was 0, right? Because I showed this in the static case. Okay, and because J, P are continuous quantities, okay, this constant has to be 0. Okay, because this needs to always be true, including in the static case, so it means that this constant is 0, and so this is still true in the dynamical case. And this is the argument on why I will be able to use this equation in everything that follows. Okay. Okay. So this. The first part, I forgot to write it. So this polarization in materials. Okay, and now the second part will be, I will present you a model which is called the Lorentz model, which you might also have heard about in the. Did you hear about it in the course about waves? Model Lorentz. It's a model where I have an electron which is right. An electron which is attached to the nucleus with a spring. Do you remember? Okay. Okay. So. The second part is the Lorentz model. Okay, and the idea is that what we want to do here is the question we're asking is, how does my material react to the electromagnetic field that crosses it, okay? So we showed that many of the things we already know about the polarization, we will be able to use it, we will be able to use the polarization formalism, but still I'm asking, okay, what is the reaction? How does the material react to a dynamical electromagnetic field? Okay, and this model is a phenomenological model. It's not a perfect one because in the exact same way that the model we had in the static case with the cloud of negative charges and the positive charges, it's wrong because it doesn't use any quantum mechanics. Okay, this will be the dynamical equivalent of what we did already. And the thing is, it's a very good model because it will help us understand qualitatively many of the things, like, for example, absorption. Okay, absorption lines can be explained with this very simple classical model, which is the reason it's so useful, but we will always keep in mind that it's fundamentally wrong, okay? Because it's classical. So what are the hypotheses of this model? So the first hypothesis is that I'm looking at some gas, okay? And this gas is monoatomic and is only made of hydrogen, okay? So everything which we will say about waves in materials within this model is actually waves in hydrogen, okay? Monoatomic hydrogen. Gas, hydrogen, okay? There was a question? No? Okay. The second hypothesis is that, or definition is that the density, the number density of particles in this gas is given by rho n. Okay, and this is the important part. So each atom in this model is modeled. Each atom is modeled as a positive nucleus, okay, a negative cloud of electrons, okay, and the cloud is bound to the nucleus. Okay, so until here it's pretty similar to the model we had in the static case. Okay, but what will be very special is that this bound will be an elastic bound, okay, like a spring. Okay, so I will model this bound like Kesher Fritzi, okay?
So there is always a J, but there is always a change in the density.
Yes, there will be yes.
Okay.
Okay, so I'm still describing the model. So we have an exterior field, okay, which in the static case was this constant E0. If you remember, we had this small diagram, E0 plus E1, made all these boxes, and this is in terms, you remember this? So E0 is now changing in time. Okay, so the external field I'm applying is the following. I'm writing it in a complex way. So it's equal to E0 m exponent of minus I omega t. Okay, I'm taking a monochromatic, an harmonic wave here. Okay, monochromatic sinusoidal electromagnetic wave as the external field. Okay, and I'm asking what happens under this external field, what happens to my atom? Okay, so so if I have the initial position of the cloud, so this is no, it will be the opposite. So if this is my, I'm starting with here a positive charge, and the center of mass of the negative charge is at the same place. Okay, and now the negative charge is moving away, and P, okay? So this is, so the new position of the negative cloud is this, okay? And I will introduce a small vector which I will call ER, which is the displacement, okay, the relative displacement of the positive and negative parts of the atom. Okay, so ER of M and T. This is the displacement, the relative displacement of negative versus positive charges in the atom. Okay, and this is it's a displacement relative to the equilibrium position. Okay. Okay, so until here, everything looks very similar to the classical model we did in the static case, except for this part. Okay, and the fact that here I have this time dependency. Okay, now the sixth part of the model, which is very important, is if I look at the forces, I'm asking, okay, what are the forces that are acting on my atom? And here this model has a very strong claim. Okay, so the first force, this you know. Okay, I'm not making any assumption here. Okay, what are the forces that are felt by the negative cloud? Okay, so the Lorentz force F, which is equal to E plus V plus B. Okay. Now, if I make some order of magnitude calculations inside the electrons, the velocity of the electrons in a classical depiction, do you know? Do you have an intuition for it? 10 to the 7, 10 to the 6 meters per second. Okay, and B, we saw that this is E over C0. Okay, so it's E over 10 to the 8. Okay, so it means that this term is about E over, it's 100 times less than E. Okay, so this term is 100 times less than this term. And that's why I will neglect it. Okay, so I will assume that F is approximately EE. Okay, so this is the first force. The second force, and this is a very strong assumption of the model, is the force that links together the electrons, clouds, and the nucleus. Okay, and so I will call it F binding. Okay, when I talk about bound charges, this is exactly what bounds. This force is what bounds them. Okay, and this I will assume has the shape of a spring force. Okay, so this is not the wave. It's not the wave, the k of the wave vector. It's the k of the spring. Okay, and because it's confusing, I will not remain with this notation. Okay, I will. You remember that k, in the case of in mechanics, it can also be written. We saw that we have an oscillator, and it can be expressed as a function of some pulsation and the mass of the spring. You remember? So this is minus the mass of the electrons, some pulsation, ER. Okay. Okay, and this too. This is not the omega that's in my wave. Okay, it's not this omega. It's some pulsation that is specific to this binding force, to this spring. Okay, and in a sense, it's a property of the material. Okay, property of the material. Okay, it's very important because the fact here that we have two pulsations, because we will see that they are linked to each other. So when I will excite the material with a pulsation that matches this pulsation, I will have some very interesting behaviors. But it's important to remember that they are fundamentally different. Okay? So this is the second force, and I have in this model, I have a third force that describes the dissipation of energy. So maybe you remember from mechanics, how do we write these forces, these damping forces that describe some energy dissipations? They are proportional to what?
Minus gamma Q. minus gamma t.
Right, they are proportional to the velocity. Okay, so I have C, the third force, which I will call F damping. Okay, which describes the fact that my system is going to lose energy. Okay, and it's minus gamma. This gamma is also, I also have some mass dependency, dER over dt. Okay, and here too I can write it as a function of the pulsation. Okay, I'm opening this gamma here, dER over dt. Okay, and so these two are properties of the medium. Properties of the medium. Okay, so in terms of forces, the three ingredients of these models are the following: just the electric, the Lorentz force, which I can approximate, some force that binds the electrons and the nuclei together, and some force that describes the fact that the system is losing energy whenever it's moving. Okay? Okay, so now let's just write what Newton tells us about this. Checking how far I need to get for the break. Other questions on the hypothesis of the model? Okay, so let's write the Newton's equation. Okay, so what does the Newton's second law tells me? Okay, it tells me that ME, you tell me.
As acceleration.
Right, but I can write it as a, I'm going to try to translate it in my model. So here I have a second derivative of ER, this is the displacement vector, is equal to what?
The force, so it would be Q, the charge.
Okay, so this is minus E because I'm doing it on the electron cloud, okay? And then, what else? Minus ME, the pulsation square ER, right? Minus 2 eta ME, the pulsation, dER over dt. Exactly. And I'm going to do now one last assumption, okay, which is the fact that we will assume that ER is also some sinusoidal, follows the sinusoidal dependency with the same pulsation as the field that excites it. Okay, this is a pretty standard assumption that we do in mechanics. If I have some external constraint that excites my system in a sinusoidal wave with a certain pulsation, I'm assuming that the reaction of the system will follow the same behavior. Okay? So I will assume that ER is equal to E0M, exponent of minus E omega t, which means that, so the amplitude is a function of space, and all the all the time dependency is sinusoidal with the same properties as the field that excites it. Okay, and so this, it's important. This is the same pulsation as in what? In E. Okay? Okay, and so I will be able to rewrite this using the magic of the complex notation. Okay, so I'm getting that ME minus omega square ER is equal to minus EE minus ME omega square ER minus 2 eta plus 2 eta ME omega 0 I omega ER. Do you agree? Yes? Okay, and so if I move everything, if I isolate ER, I have that ER is equal to minus E over M times E minus omega square plus omega 0 square minus 2 eta omega 0 omega, and here I also have I. Okay, and in some books I know there is a different convention here, that there is a plus here. This is just a matter of how we define eta. Okay, so if you come across this convention, it just means there will be a plus here. I think in the Griffiths it's the opposite convention. Okay, and so now I will define, let's define this omega tilde, okay, which is basically giving me a comparison between these two pulsations. This is the pulsation of the external constraint of the field, okay, and this is a pulsation that expresses an intrinsic property of the material, okay, the way the material will react. Okay, this is the pulsation of the string, okay. And so if I introduce this this quantity, I can write that ER is equal to minus E M E omega 0, this ME omega 0 square times E divided by 1 minus omega tilde square minus I to eta omega tilde. Okay, so what I wrote here is a relation between the external field, the external constraint, and the displacement, the relative displacement within the atom. Agree? Good. Okay. Now, I remind you that whenever I talk about electromagnetism and materials, the name of the game, at least in the first, when I had these 3 boxes, the name of the game is to try to link the external field to the polarization, right? Because if I do this, I can then express the polarization as a density of charges, etc., etc. Okay, so let's try to link this to P, to the polarization. Okay, because eventually the polarization is what I'm using, is the formalism I'm using to express the relation between the external constraint and the reaction of the material, right?
Isn't it just this ER times the
It is, so remind Ariel? Yes? So Ariel is saying, very easy. ER is the displacement of the negative and positive charges. And I know how to write the polarization as a function of the dipoles, okay, the atomic dipoles. So this is going to be super easy. And she's right. Okay, so I know that the small dipole moment within the atom is Q and P. Okay, and this NP is precisely the displacement, right? This is the negative and positive center of mass. So the P, the small p, the atomic dipole, is going to be minus ER, right? Okay, so here I did some assumption. What did I assume? I assumed that that NP, what I wrote here is for the electron, right? I wrote the Newton's law for the electron, right? And here what I'm saying basically is that NP is the movement of the electron. And why is it true?
The electron and the proton is the same, it was an opposite charge.
Yes, but also because of the masses are so different, right? The mass of the protons are so much higher than the mass of the electrons. All the inertia is going to go to the electron. So really what is moving, when I talk about the displacement, it's mainly the negative charges that are moving. The positive charges are hardly moving because of the difference in the masses. Okay, so here I've assumed, okay, there is a hidden assumption that only the negative charges are moving and charges are moving. And this is true because the mass of the proton is so much higher than the mass of the electron, so this is a good approximation. Okay, so once I have this, I can write a complex individual dipole, okay, which is, okay, I'm just replacing here. So I'm adding I here to write that it's the individual ones, the atomic ones. Okay, so I can write that this is going to be plus E squared divided by ME omega square 1 minus square minus 2 eta I tilde. Okay, and the polarization, how do I write it? It's rho n pi, right? So it's going to be equal to rho n e square over 1 minus okay, so this makes us happy, okay, because what we wanted to do is to link the polarization. Okay, the polarization, it quantifies the reaction of my medium, and I want to link the reaction to the source, to the cause. Okay, so this is what I did here with this very simple model. Okay, and if you remember, we defined in this relation a quantity called the susceptibility, right? So now I will be able to define a complex susceptibility. Okay, the susceptibility was precisely this coefficient that linked E and P in the static case. So the complex susceptibility, it's now going to be quantities that depends on the pulsation, okay? And it's equal to rho n E square 1 minus delta I tilde. Okay, and so if I define this, I can write that the complex polarization is equal to epsilon 0 complex susceptibility times E. Okay, and these are all very important formula.
Marianne, can you remind what's the rho n stands for?
What?
The rho n?
Rho n is the density of particles, of atoms in the gas. So in the list of hypotheses I made, it was the second one. Rho n is just how many atoms do I have in my hydrogen. Okay? Okay, so here I'm going to make several comments. Okay, so first comment is that part of our goal, I'm saying it again, but part of our goal was to link E and P, and with this very simple model, I managed to do it. Okay? So I managed to link the reaction of the medium to the external constraint. Okay?
The susceptibility is complex, is helping us here. What does it mean?
Okay, so this was my second comment. Okay, before this, I will do a preliminary comment. So you see that the Lorentz model, it leads to a linear relation between the polarization and the field. Okay, there's a linear relation between the constraint on the medium and the reaction of the medium. And if you set omega to 0, we are back to the static case. Okay, you can check it. So if I have a, okay, you agree? We are back to the static case if we set it to 0. And so Ariel asked me, what does the fact that this is complex what will it mean physically speaking? And so this is a very important point. When I talk about proportionality in complex, it's not quite proportionality, because this it means that P and E are proportional up to a phase, right? You agree? If this is a complex quantity, it means that if E is harmonic, P will be harmonic, and they will be proportional up to a phase, up to a difference in phase. Okay, so the complex amplitude will not be quite completely proportional. Okay, so this is a very important comment. So the fact that chi is complex, it means that there is proportionality between E and P up to a phase. Okay? And we also showed that key E stationary is equal to key 0. Okay? Okay, so now okay, and now we will dive deeper into this function, okay? Because once we've said that the Lorentz model leads to some linear relation, this is one important and interesting thing. But the shape of key, okay, from this, I can draw many information on how the material reacts to the field. Okay, so now let's decompose key into its real and imaginary parts. Okay, I actually, what I want to do is to look at this function. How does it look like as a function of omega? Okay, because this is actually going to tell me the physics of the, this is going to answer Ariel's question and tell me how does the shape of key and the fact it's imaginary, how will it impact the physics, the physical behavior of the material. Okay, so let's decompose key, okay, into its real part and imaginary part. Okay, so key is equal, so key dot plus I. Okay, I'm using these dots here as the real part and imaginary part. Okay, and how do all this? So you can write it. Okay, you can do it. You can basically bring this up with proper multiplication and decompose it into two parts. And if you do it and you look at the shape, I'm going to tell you what the shapes of these two functions is. Okay, so I have chi prime, which is going to look like this. Okay, and this is 1. Okay, so I remind you that tilde is omega over omega 0. Okay, so when the pulsation of the spring in my model is equal to the external pulsation, the real part is going to be 0. Okay? And the imaginary part will look like this. Okay, so what does it tell me? Let's try to translate it into physics. Okay, what happens when I excite my gas of atoms with a sinusoidal field that has exactly the same pulsation as some intrinsic pulsation of my material, which is the pulsation of the spring? Yes?
The phase between the polarization and the field is exactly 90 degrees parameter.
But from these functions,
yeah, you can say that the real part is 0 and the imaginary is not 0. So
yes, but it's not only non-zero, it's very, very high.
You also have a resonance.
Resonance, exactly. This is exactly what I wanted to hear. Okay, so it's 1 or 2 n, you know? Resonance with 1 or 2 n's?
I think it's 1, but let me check.
Okay, so when I excite my material with some specific pulsation, okay, I will have a resonance effect. Okay, now what is resonating? It's some resonance in chi, right? So it's also in p, right? But it's also going to be in the value, right? Because the real part is, okay? So chi will be in value, it will be maximal, okay? And so because this will be maximal, P2 will be maximal, will be resonating. And it's also in ER, right? So the displacement of the of the relative displacement within the atom will also be reaching some extreme, okay? So, okay, so when omega is equal to 0, I have some extreme displacement within the atom. Okay, and the reason I'm emphasizing this is that what we will do after the break is to take one step back and look at all of this from the point of view of the field, okay? What we did until now is to ask, okay, well, how is the medium reacting? But I will also want to check how is the field, okay, the electromagnetic wave that is traveling within the medium, it will also be affected by the medium, right? And so the question will be, okay, how will the field be impacted? And this resonance in the reaction of the medium, it will have to appear too in the expression of the field, okay? And if I go one step further, at this, in this situation, I will have some maximal transfer of energy from the field to the medium, okay? So the area around omega equal to omega 0, okay? This is called the absorption zone. Why absorption? Precisely because of what I said now, because this will be the area where the field is translating into some extreme maximal reaction of the material. Okay. I'm checking. Okay, so maximal amount of energy will be absorbed by the medium. Okay, so this is where the maximal amount of field will be converted to kinetic energy, basically. And it's pretty amazing that this small model, very simple model, is allowing us to reach this. Okay, we're actually showing with this simple model that there is such thing as absorption lines. Okay, this should blow your mind. Okay, we cannot show, what we cannot show is that there are several absorption lines in hydrogen. Okay, because for this we need some quantum transition, etc. But we can show with this super classical simple model that there are hydrogen absorption lines, and this is pretty amazing. Okay, so I think it's almost time for the break. So let me just define one more quantity here. Okay, so we've defined the permeability in the stationary case, right? So I will now have some complex permeability. Okay, 1 plus Ke omega. Okay, and this is equal to E. These are all definitions. Okay, and one more comment that I want to do is that if I want to generalize this to some material where I have several types of atoms, okay, not just hydrogen, this was one comment, and the generalization to several types of atoms is the following. Okay, this will be the sum of KEI 1 divided by, so the pulsation here, I will have one different pulsation for each type of atoms, okay, because this is what characterizes the atom, okay, minus 2I eta omega divided by, okay, and this here is going to be rho n I e square. Okay, so this will be a sum. And why is it going to be a sum? Because when I want to calculate the total dipole moment, I make a sum of all the small dipoles, right? So this is where the sum will appear, and this is what will allow me to generalize this. Okay, so one more comment is that this simple model explains the phenomenon of absorption lines. Okay, what it doesn't explain, but does not explain the existence of several absorption lines. Several of them, or of multiple lines. Okay. Okay. Very often, the mediums that are well described by these models are called DLHI. I don't know if you came across this. So this is for dielectric. This is for linear. This is for homogeneous. And this is for isotropic. So sometimes in exercise you will be told, okay, your medium is a DLHI, okay, and this just means that you can apply what we showed here. Okay, so and this homogeneity and the isotropy, it basically means that phi doesn't depend on the point in space. Okay, phi independent of space, location, or direction. Okay? Okay, and the last comment before the break is that because chi depends on rho n, what is rho n? It's the density of atoms, right? So because chi depends on rho n, it will also be sensitive to all kinds of thermodynamics conditions, right? If I change the temperature or the pressure, rho n will change, right? And so the susceptibility of my material, the reaction, the way a given material will react to some field and the area where it will absorb, etc., will also change. Okay, so chi is sensitive through rho n to the thermodynamics, thermodynamic condition. So the temperature, the pressure, etc. Okay. Okay, and okay, I will do one more comment because after the break I want to change slightly subject. So the last comment is that I can define in the same way, because all of these things are complex, I can also define a complex quantity for the current. Okay, so J, the current of polarization. Okay, so this is the current that is related to the polarization, and we showed earlier that this is dp over dt, okay? And I can write it also as a function of the susceptibility, okay? Key. Okay, so when I have some resonance in key, I also have a maximal amount of currents, okay? And if I have some harmonic dependency of E, the currents too will be harmonic, okay? So if E harmonic, G, the currents too are harmonic, etc. Okay? And there is a proportionality up to a phase. Proportionality. So key acts on the phase of G. Okay? Okay, so these are all the comments I wanted to make before the break. And after the break, we will look at all of this from the point of view of the field. How will this affect the field? I'm going to write this. Okay, so what did we show before the break? We showed several things. Shall we very quickly summarize? Okay, and we showed that the Lorentz model tells us how a material reacts to some external electromagnetic wave. Okay, so the Lorentz model. Tells us how a material reacts to an electromagnetic wave. Okay. We saw that most of the reaction that we're talking about is a reaction in E. Okay. So most of the materials reaction is to E. Okay? And we saw that we can write the polarization, which quantifies this reaction, with the parameter key. We can express P with the parameter key, which depends on the material, right? Through what? Through omega 0, right? And through eta, and through m, or not m, because m will be the same for all the material, but through mostly omega 0. Okay, and it also depends on omega, which is the pulsation of the external field, right? And we saw, so this, by the way, this should remind you of what you know about dispersion, okay? I will have a different, if I have an electromagnetic field which is composed of many, many different frequencies, the reactions will be different for all these frequencies, okay? And I have some resonance phenomenon, okay? If E pulsates at a frequency, a pulsation omega 0, which is the pulsation characteristic of this material, okay? We will have a maximal movement of the electron, okay? And this phenomenon of resonance, we showed it from the point of view of the atom, but really it should be visible also in the field. Okay, this is an important point. So if it's not clear, let me know. Okay, if the material reacts in an extreme way, I should also see in the shape of the wave something happening at this frequency. Okay, this is what I will show now. Okay, so this should be visible at the level of the field too. So can you guess what kind of manifestations of this can I expect? Okay, if the material absorbs a lot at this frequency, okay, what can you guess about the shape of the field, of the electromagnetic field? The electromagnetic wave is being absorbed at this frequency. Can you guess what it will mean? When I will write the electromagnetic wave, what will it mean? Okay, so I will probably have some factor that will express some deicha, right? Some attenuation of the wave. And if I look at the pointing vector, for example, I can also expect something, right? That the function that describes the amount of energy that travels should also be very attenuated at these frequencies, because it basically means the field will be losing its energy to the material. I'm trying to make you feel the intuition of the physics before we go into the hardcore of the formalism. So you agree? I'm expecting some term of attenuation when I'm looking at the wave. Now, if I have some attenuation, it's not quite a wave anymore, right? Because you remember when we spoke about waves last time, what did we say? We said that a wave is a perturbation that travels unchanged through a medium, right? You remember we said this? So the moment it's attenuated, it's not really a wave anymore. It's a pseudo wave, okay? And this is what we will derive now. Okay, so what do I do when I want to? What is my recipe when I want to derive something about the structure of the electromagnetic field, of the electromagnetic wave in somewhere? What do I write? What do I start with? So last time when I wanted some wave equations, right? When I wanted to derive the wave, the electromagnetic wave, I started with the Maxwell equations, right? So I'm going to do the same. Okay, so the title here is the structure of the electromagnetic wave, and I'm putting here Gersheim because we will see that it's not going to be quite a wave anymore in material. Okay, and let's just write the Maxwell equation, which we already know. So div of B is equal to 0. Divergence of E is going to be rho bound over epsilon 0 plus rho free, but rho free is 0. Okay, I'm assuming I don't have any free charges. And rho of B is mu 0 J bound plus mu 0 epsilon 0 dt E, right? And rho of E is equal to minus dt B. And if you remember throughout this course, every time we were writing this and then we were dropping something because it was, oh, we're in vacuum, or oh, we're in the static case. So we've now reached the point when we're not dropping anything. Okay, we're using all the Maxwell equations now. Okay, and the other equations I will be using is that divergence of the polarization is equal to minus rho bound. This I showed earlier today. and J bound is equal to dP over dt. Okay, and this is how the polarization will make its way through the Maxwell equation, through the J bound and the rho bound here. Okay, makes sense? Okay, and I can write further this as div of epsilon 0 E plus B, right? No, sorry. So this is equal to 0. Okay, you agree? No. No, sorry. Okay, sorry. Yes, div of epsilon 0 E plus B is equal to 0 because I can take this to this side of the equation, you agree? And I'm replacing rho bound by div of B, okay?
You assume that no stat.
So this, what?
You assume that there are no charges, only bounded charges?
Yes. I'm assuming I'm in a material with no free charges. What?
This is just the divergence of D.
Yes. Okay. And I can also write here a modified Maxwell-Ampere equation. I can write that rot of B over mu 0 is equal to dt of epsilon 0 E plus B. Okay? This is this. Okay? I'm taking replacing J bound. Okay? So this. Okay? So this is the Maxwell equations I have, and can we transform this equation into wave equations in the exact same way that we did in the vacuum? This is my next question. Can we derive from these equations, wave equations, okay, which it's like asking, is there such a thing as an electromagnetic wave in a material? And because of what we showed with this model, we already guessed that it's not going to work, because whatever is propagating in the material will have to be attenuated in some way. Okay? Okay, so what I will do now is I will assume okay, I will assume things are harmonics so that I can use the magics of the complex notation. Okay, so I know that grad is like multiplying by ik, and dt is like multiplying by minus I omega. Okay, so one thing I can already extract from my Maxwell equations, if I take this equation that rho of v is minus dt of b, I can already write, I don't know if all these arrows make sense, but I can write that ik rhos e is equal to I omega b. Okay, so b is equal to k divided by omega cross E. Okay, and this, I remind you that I want to guess the structure of electromagnetic waves inside the material, so this is already giving me some information about it, right? That B is going to be orthogonal to both the direction of propagation and E, right? So B is orthogonal to K, it's orthogonal to E. If you remember, we said that this was also true in vacuum. Okay, but what will not remain true is that in vacuum, E too was orthogonal to everything, and this will not be the case now anymore. Okay, and now I want to check if I can make some wave equations. Yes.
The definition of the derivatives is with assuming that our function is a wave.
Yes,
We just said it's
not
not
just
a
a wave, harmonic wave.
But we said that the solution is not a wave, it's decaying.
Right.
So it has to be some other factor in the derivatives.
Right.
It explains you can say it's a wave with a complex K vector.
Although yes, I mean you can also show it in. Remember that last time we showed in two different ways the structure of the waves. One time we assume harmonic shapes, and one time we didn't. We did it with the with the plane progressive too. Right, so knowing the shape of whatever is propagating, it will work, but we should check it at the end. Okay? We should make sure it's true at the end. Okay, so now let's move to the hard part of the work and try to derive some wave equations. We will finish at 11:40, okay? Okay, so what do every time I'm trying to do this, I'm basically taking the root of this, if you remember. Okay, no, sorry, the root of this one. Okay, so I remind you that root of root is equal to grad of div minus Laplacian, okay? And okay, so what it tells me is that so if I combine this equation, it will tell me that grad, I'm taking the root of this, okay? So the gradient of div minus Laplacian of E is equal to minus I omega root of B, okay, which is minus I omega plus I am also using Maxwell Ampere. I'm using this one and this one here. Okay, so this is plus I omega mu epsilon. You should check that you agree with me, okay? Okay, so this gives me that Laplacian of E plus omega square over C0 square 1 plus chi epsilon is equal to 0. Okay, and Laplacian of B, I didn't show it for B, but you can do it, it's the exact same logic. Okay, so I'm getting these two equations. which are obtained by basically assuming a complex shape for E and B and combining the Maxwell equations in the same way I did before. Okay? And another way to write this, okay, another way that I can write it is that Laplacian of E, of course, all of these are complex. Okay, so Laplacian of E is equal to E mu 0 d dt over dt2. Okay, where this E is complex is equal to epsilon 0, 1 plus K. Okay, this is just another way of writing the same thing. Okay, so this looks like wave equations. Okay, it looks very much like wave equations, but it's not wave equations because this is complex. Okay, this is what makes it different from the normal wave equation that we know, that we are used to. And the solution to this wave equation is what we call a pseudo wave. And I will write now the general solution, and we will have to accept it. Okay. In the case of the wave equation, I showed you that the shape of the solution, but here we're just going to accept them. Okay. So the solution is a pseudo harmonic wave. Okay, and this is how it writes: E n t equal to E0 exponent. This is where it's working. The derivatives are working as we explained, but it's true that it's a bit it's cheating a bit to just say it now. Okay, so I k uk minus omega t. Okay, where this wave vector is complex. Okay. Okay. Now let's. You remember that in order to obtain the relationship between the wave vector and basically the dispersion relation, what we do is we put this into the wave equations, remember? So we're going to do the same. We're going to put this into this. Okay, so if we inject this solution into this equation, which reminds us of a wave equation, what do we obtain? We obtain that k complex square, okay, you should check that you agree, is equal to omega divided by C0 square, 1 plus k, okay? And this is what we will call K0. This is very important. Okay, so K square is equal to K0 square, 1 plus K. Okay, so the complexity of K comes from K being complex. Okay? And this is why this is important. This is a wave vector in vacuum, right? You agree? It's just the shape of the field divided by the velocity in vacuum. Okay, so this is just the wave vector we know. Okay, so the complexity of K comes from K being complex, right? Okay, and now we will write K in a slightly different way. We will define N. Okay, so K complex is equal to N complex times k0. Okay, so you already see that n square is equal to 1 plus k. Okay, this is the permittivity. Okay, you agree because n square is k over k0 square, and it's exactly 1 plus k. Okay, and now a very important thing, we can decompose n as its real part, okay, plus its imaginary part, okay, and this is called n, and this is called kappa, and this is, you know what this is? N, sorry. This is the refraction index that you know, okay? This is the refraction index, okay? And this kappa is the absorption index. And you can already guess that this attenuation term that I told you, which should appear somehow in the wave, is going to appear because of this. Okay, precisely because of the imaginary part, because of the complex contribution to this wave. Okay? Okay, so with this definition of n, I can rewrite, let's rewrite this shape, okay? My goal is to write the wave with some factor that will attenuate it. Okay, so let's rewrite E of M complex. Okay, it's going to be E0 times an exponent of minus kappa K0 UK OM. Okay. Time an exponent of I n K0 UK OM minus omega t. Okay, so this is what? This is just a harmonic. This is just a harmonic wave, right? In complex notation, everybody agrees. Okay, this is just a harmonic wave. Harmonic wave, and this is also the k in vacuum. So it's almost nk0. K0 is in vacuum. So this thing here has a shape of a harmonic wave, where the wave vector, instead of being k0, is k0 times n. You agree? Yes? Okay. And this is an additional factor. Okay, so one thing that we showed is that indeed the solution of this is not a wave. Okay? If it was a wave, it should have the shape that we're familiar with, and it doesn't have the shape. So the solution of the propagation of electromagnetic fields in a material is not a wave. Okay? Now, can we say that this is an attenuation factor, or what are we missing in terms of what is missing in our demonstration so that we can say that this is attenuating the wave? Exactly. We need to say something about the sign of kappa, right? And this is missing in our demonstration. So let's check what is the sign of kappa. Because it could also be increasing it, right? Okay, so n squared complex is equal to n squared minus kappa squared plus 2i n kappa. Okay, this is just by definition of n. Okay, and this is also equal to 1, this I will let you check, okay? this is also equal to 1 plus key 0. This was the upper part of key that we wrote. Okay, 1 minus omega tilde minus 2i a omega. Okay, this is just what we derived for key. Okay. Now we remember the shape of key, right? We remember that the real part of key is like this. Okay, and the imaginary part of key is positive, right? So if we identify, okay, so here this is real. Here we have some real part that looks like this, plus some positive imaginary part. Okay, so if we do the identification, it means that 2n kappa needs to be positive, right? You agree? And so this is positive, and n is positive too, right? Why? N is positive because this is just a choice, because we are looking at a wave that goes in a specific direction, in the direction of UK. Okay, and when we write a harmonic plane progressive wave in the direction of UK, within our convection, this part here needs to be positive. Okay, so n is positive. Okay, so kappa is positive. Okay, and if kappa is positive, it means that this part here is indeed an attenuation factor. Okay, so and this is what we wanted to show. Okay, we wanted to show that just as we would expect from the fact that the material is overreacting at some specific pulsation. Okay, it's overreacting, it's absorbing energy. The wave feels it and is being attenuated at this specific pulsation. Okay, and I will finish by, I told you that we could also expect something about the Poynting vector, right? So I will not write the full demonstration because we're reaching the end of the lecture, but I will give you the result of, and you can also do it at home, of what expression you should derive for the Poynting expression, for the Poynting vector, and why this attenuation is visible in the Poynting vector too. Okay, so if I look at the Poynting vector, okay, P is equal to E cross B divided by mu 0, okay, and this, you should check it's maybe 3 lines, okay, this is N divided by mu 0 C0, exponent of 2 kappa K0 square, okay, times a cosinus of something, so here you will have a cosinus of something, here you will have another cosinus of something, and here you will have E0 UK. Okay, and then if you take the average value of the Poynting vector, you will get that this is n divided by 2 epsilon 0 C0 exponent of 2 kappa K0 Z E0 squared UK. Okay, and these two, because we showed that kappa is positive, is also an attenuation factor. Okay? So we closed the loop.
You don't need the minus sign?
Yes,
A minus?
Yeah, it's positive.
Yes.
Or you can
No,
also
there
say
should
that
be
is
a
negative.
no.
You can say
There
that E
should
operator
be
is
a minus.
negative.
So, okay, so now we close the loop. Okay, and next time we'll be on Zoom and we will talk about radiation. And then lecture 10 and 11 will be about relativity, but will not happen in this very weird and specific semester.
Zoom in 2 weeks?
כן, יש רק, no. There is just one lecture, okay? We're basically skipping the last two because of the shape of this semester. So there is one more lecture in 2 weeks on Zoom. Next week I'm going to a conference, so I will do the one after from abroad, but just in the conference it's a bit complicated.